Okay, I would like to welcome everyone to the last session and the last lecture of the school, when we will finally hear about correlation function and how to compute them at finite coupling in n equal to 4 superangles.
Yes, we are going to finally hear about it. So let me first review what we did in the previous lectures. So in the lecture 1, we discussed the ON sigma model, and we derived the 2, 2, 2 S matrix by imposing the Yang-Baxter equation and unitarity and crossing symmetry. And then in the lecture 2, we saw how the spin chain arises from n equals 4 super mu theory by doing a one-loop computation of the two-point function. And then in the last lecture, I discussed how to generalize that kind of idea to finite coupling and compute that two-point function at finite coupling. And essentially, the key idea was to use the little group, the idea of little group, together with large gauge transformation. And I discussed that if you combine these two ideas, then you get what is called the centrally extended PSU2/4. Sorry, PSU2/2 squared. And by imposing the invariance of under PSU2/2 squared, you can determine the S matrix on the spin chain. Especially, you can completely determine the matrix structure of this matrix of the spin chain, especially 2, 2, 2 scattering. And there is an overall factor which I didn't really discuss, but I just mentioned that you can determine this overall factor by imposing unitarity and crossing, as in the case of ON sigma model. And once you determine the S222S matrix, you can use that 222S matrix to factorize the multiparticle S matrix by assuming that the theory is integrable at finite coupling. And that leads you to the beta equation at finite coupling. And by solving the beta equation, you can determine the energy of the spin chain, which is equal to the anomalous dimension at finite coupling. And by doing so, you can basically compute the two-point function at finite coupling. And the last lecture, we are going to generalize this idea to a more complicated observable. And the title of the last lecture is how to make a pair of pants. So you might think that why I started talking about a pair of pants, but you will see soon that a pair of pants is actually relevant, and relevant for the computation of the three-point function in n equals 4 super mu theory. So let me remind you that n equals 4 super mu theory is conformal. Therefore, the important in the conformal field theory, there are two important observables. One is the two-point function, which is basically determined by the dimension or anomalous dimension. So this we discussed in lecture 2 and 3. And there is another important observable, which is the structure constant. So the space-time dependence, I think you can find it in your note, is determined completely by the dimension of the operator, but there is the extra input, which is called a structure constant. So what I'm going to do today is to compute the structure constant, now again using the spin chain description. So, and to do that, again, as we did in the second lecture, I first start from the weak coupling analysis, especially not today. Well, in the first half of my lecture, I'm going to just talk about the tree level, so it should be easy. But even at tree level, you can actually find a nice structure, and which leads us to a finite coupling conjecture. Okay, so now I can move the board. Okay, so now the three-point function. And the starting point is to analyze the tree-level three-point function. And see how the spin chain emerges, or how the spin chain plays a role in the computation. And to simplify our life, I'm going to talk about very specific three-point function in which operator O1 is the one we discussed in the lecture 2. So it's made of maybe lecture 3, or well, I think it's lecture 2. So it's sum of this kind of operator, and of course, and as I said, by using a map to the spin chain, this operator is mapped to the spin chain state, and I impose that this sum basically produces the eigenstate of Hamiltonian. Or, in other words, it's the eigenstate of the anomalous dimension matrix. So in order to have a good behavior like the one I wrote, well, it's hard to see, but in order to have a good behavior of the space-time dependence, I need to impose that this object here is an eigenstate or under the dilatation operator, or I need to impose that this object has a definite anomalous dimension. So, and for the operator 2, I kind of choose a very trivial one, which is trace of z bar to L2. Okay, by the way, let's denote the length of this guy by L1. So the operator 2 is a kind of trivial, which is essentially the same as the ground state of the spin chain. So it's just a conjugate of the usual ground state, which is made up of just z. And for the operator 3, I again take a trivial one, but in order to have a non-trivial three-point function, I choose this z twiddle to be z plus z bar minus y minus y bar, where z and y are the complex scalars contained in n equals 4 super mu 3. So this is the three-point function I'm going to study. And the first step, well, okay, actually, to compute the three-point function of this guy, especially at tree level, what you just need to do is very simple. Because we are at the tree level, it's just a weak contraction. And the important point here is that because we are in the large n limit, the weak contraction preserves the order of the trace. So especially, you are only allowed to weak contract, for example, in this way. So again, I'm using a pictorial notation where the trace is represented by the circle, and each dot basically corresponds to each field. So this is a kind of weak contraction that we need to do. And one point I should make is that the number of weak contraction between pair of operators is actually completely fixed by the length of the operators. For example, in this case, this number, let's call it L13, is L1 plus L3 minus L2 over 2. And similarly, you can write the equation for the L23 and L12. And essentially, the reason is simple because we have like 3 variables and there are only 3 unfixed variables. So you can completely solve for it. Okay. So another good thing about this configuration, well, especially it has to do with the choice of the three operators, is that you can easily see that this Z field can contract either to O2 or O3 because Z contains, O2 is made up of Z bar, which is complex conjugate, and O3 contains Z bar as well. But on the other hand, the Y field cannot contract with O2 because there is no propagator connecting Z bar and Y because they are made up of different scalars. But on the other hand, Y can contract with Z twiddle because the twiddle contains Y bar. So this means that, okay, let's denote Y's, so which are the excitation from the spin chain picture. Then I can say that essentially y's can only live on this segment. Do you understand? Okay. So this gives us a very simple way of computing this three-point function. So this basically says that this three-point function should be proportional to sum of wave function where n1 and m is from 1 to L13. Okay, so I need to explain what I really mean by this wave function. To do that, I need to remind you what the relation with the spin chain and the operator. So the relation with between the spin chain and the operator is, as I said here, if you map z to up spin and y to down spin, then this operator maps to the spin chain. And the wave function I'm talking up here is precisely the wave function in the spin chain. So to be more precise, in the operator language, I declare that this operator is sum of the operators, and this n1 and m is from 1 to L1, where L1 is the total length of the operator, and then this is the trace, and I have lots of z's, and at n1's position, I have y, so this is n1, and similarly, there are m and my's, and the rest is z. Maybe I should move a little bit. So, and this wave function psi is precisely this wave function. Is this point clear? And okay, so I should also say that I'm choosing the starting point of the spin chain to be here. So this is the first side. And this is the L13 side. Okay, so this is essentially what we need to compute at tree level. So it's actually conceptually very simple. I just need to know this wave function and then do this simple sum. And let's see how this sum can be, well, let's see what we get by doing this sum for simple cases. So, of course, the simplest case is just having one y, but it's a kind of too trivial, so I would choose m equals 2 case, so that there are only two y's. As I explained in the previous lecture, in that case, this psi of, okay, let's call it m and m, is sum of two plane waves. And the first term is e to I p1 n plus I p2m. And the second term is s p1 p2 e to I p2n plus I p1m. And this, physically, this has interpretation of the S matrix. Yeah, I'm not going to write down the explicit expression of this matrix, but I think you can find it in the notes of this lecture too. Okay, so essentially what I need to do is very simple. I just kind of take this expression, which is just exponential times something, and then do this sum. So let's do the sum one by one. So because it consists of two parts, so I first consider the sum of this guy, and then later add the contribution from the other term. Okay, so let me just erase. Okay. Now, let's do the sum. But before okay, so essentially, the sum we need to do is the sum of exponential. Well, and so the typical sum I need to do is something like this. So the range of k is from 1 to large K, and I typically need to do this sum, e to IPK. So of course, this is very trivial. It's almost embarrassing to talk about this sum in this winter school. And this is just a geometric series, and you can easily show that this gives you this structure, where G of P is, if I'm correct, e to minus IP minus 1 over 2, 1. So there is some reason why I wrote in this way. And the reason why I wrote in this way is because I want to have some pictorial notation of this sum. So the idea is to write a segment of length k, and then denote this exponential e to IPK by putting a point at the position k. So this is my notation for this exponential. And essentially, what this formula is telling you is that up to overall factor G of P, if you do the sum, then essentially the result consists of two terms. And in one term, the particle is living at the left edge, and in the other term, the particle is living at the right edge. So this is just a pictorial notation of the geometric sum. But this later proves to be very useful when you want to kind of understand the physical meaning of the sum, well, the result of the sum we get. So let's do the computation. Now I'm not sure which blackboard I should erase. Okay, but maybe I should erase that one. And then I will move this up. Sorry. Okay, so let's do the sum for this guy. And now I have, so if I use the pictorial notation, then I have something like this. So the length is, the total length is L13, and then I have particle here at nth position, and the particle here, okay, let's use a different color. The second particle, which is red, at here. Of course, you can easily do the computation by doing for example, using Mathematica. Okay, I think you can do it without Mathematica as well. But let's first do the sum of n. Then, and also forget about the overall factor G of P. Then, if you do the sum of n, then what you get is, of course, two terms, where the first term, these two particles, sorry. So in the first term, this white particle is living at the left edge, whereas this red particle is, of course, because I didn't sum over n, is still living up here. And in the second term, what happens is that two particles are essentially living at the same position, which is at position m. So, and then I can do the second sum. Okay, so let's also write the range of sum. Then it produces several terms. The first term is like this. So two particles are both living at the left edge. So this comes from this sum. And then also there is different term in which the first particle is, white particle is living at the left edge, and the red particle is living at the right edge. And this, of course, comes from this guy. And furthermore, there is, okay, and if you do the sum for this guy, then this produces also this term. And in addition to that, there is another term in which two particles are living at the right edge. So this is the result for the first term. Of course, these, so let's call it first. So this is the result for the first term. Of course, as you can see, of course, I basically omitted the coefficient. So you actually need to multiply appropriate coefficient. But essentially, this picture accounts for the exponential propagation factor. For example, for this guy, I just assign 1. Whereas for this guy, I assign 1 times e to ip2 L13. Whereas here, I assign e to ip1 plus p2 L13. So these are 3 terms that you get. And I'm not going to do the same. Well, I didn't even do the computation, honestly, for the first term, but I'm not going to do the same for the second term. But you can easily see from this figure, because the second term is actually just exchange of the first term. If you do the computation in the second term, you get another structure where the second particle is living here, and the first particle is living here. Okay? So in summary, the final result of sum over nmm for this wave function consists of produces 4 different structures, and these 4 different structures basically correspond to bipartite partitions of rapidities, of particles. Okay. So, and let me now write the full expression for this 2-particle sum after I erase this board. Okay. Okay, so because it's not dry still, so I'm going to write the result here. So the result is as follows. So you do the sum over n smaller than m, and the summation range is L13 from L1 to L13. And if you do this sum, then let's see, I basically forgot. So the final result is as follows. So the final result is, so there are some overall factor which is not very important. And, okay, let's write it in this way. Minus e to ip1L s P1, P2, plus H, U1, U2. So this is the structure. And let me first point out that, sorry, I forgot something. So this last term should come with exponential, e to ip1 plus p2 L13, L13. Okay, so this is actually L13. So essentially, these 4 terms corresponds to the 4 terms I draw there. So the leading term 1 basically corresponds to this guy, and the next term is probably this guy, and the third term is this one, and the last one is this one. And I should say what is this H. This H, the definition of this H is as follows. So if you have U1 and U2 here, the definition of H is U1 minus U2 over U1 minus U2 plus I. And here I used the rapidity variable I introduced earlier. So these U's are actually related to the momentum of the particle. So from this simple exercise, you can learn two things. The first thing is that the result is sum over bipartite partition, as I said earlier. And the second thing is that this structure seems to telling us that whenever the particle, by the way, can you see over there? Maybe yes? Okay. Well, maybe no, but this, okay, let's bring it a bit down. Okay, so yeah, okay, so I just need this guy. So there is a correspondence between these and these terms. And first of all, this seems to be telling us that if two particles are on the same side, then you need to multiply the factor h, u1 and u2. And this exponential factor is precisely we expected from the sum over geometric series. And okay, so again, here, like two particles are living on the right edge, so we should multiply h u1 times u2. And yet, in addition, there is another structure, which is precisely the S matrix here. The question is whether there is a nice interpretation of this S matrix. Yes, there is actually a nice interpretation, and the interpretation is as follows. So originally, you had a particle 1 and 2, and in this term, you need to bring the particle 1 to the right edge and bring the particle 2 to the left edge, which means that you actually need to reorder the particle because the particle 1, which was originally on the left to the particle 2, is moving to the right. And the particle 2, which was originally to the right of the particle 1, is moving to the left. So this accounts for the exchange of particle. And then, okay, so this is I'm just kind of trying to extract as much physics as from this simple computation. But of course, you need to ask whether this structure persists if you consider the multiparticle wave functions. So, but before doing that, let me just summarize. So the two particles on the same edge produces h u1, u2, and reordering produces s p1, p2, and then there is phase factors, exponential phase factors. And now you can ask if this structure persists also for the multiparticle case. And the answer is yes. So it's a bit boring computation, so I'm not going to explain the detail. But for the multiparticle case, m not equals 2, m larger than 2, the result is the same. And the final result, which basically gives you the structure constant, is bipartite partition of the particles. So we have m particles, so I need to sum over all possible way of partitioning this set of m integers into two subsets. And what I need to put here is first e to I p alpha bar L13, where this e to I p alpha bar is just the sum of pi's which belong to alpha bar. And then, so the result, each partition describes the partitioning the particle between left edge and right edge. So this is alpha, and this is alpha bar. And as I said, for the two-particle case, we need to multiply h factor when the particles are on the same side. And in fact, if you do the computation for the multiparticle, you find that what you have is something like this. So again, somewhat surprisingly, you only have H, U, UR, UJ, which is something like a two-particle interaction. So the final, and you just multiply this object with this object. So, sorry, I and J must be different, so I need to put inequality here. So, okay, so this is not everything, sorry, because as I said, there should also be reordering factor. And the reordering factor, okay, so let's write it reorder. So the reordering factor can be computed pictorially in this way. So you first put 1 to m in this order, and then you put alpha and alpha bar here. So reordering depends on the partition alpha and alpha bar. So let's say this is 1 and this is m, for example. Then what you need to do is to connect these lines, and then, okay, maybe, sorry, there might be something like this. And then for each intersection, you just multiply S of Pi, Pj. Okay, so this is the same structure as the structure of the wave function. So, but I should emphasize that this is rather striking that even for the multiparticle, and even for something that doesn't directly correspond to the wave function, it's rather the sum of the wave function, you have this kind of factorization structure. Okay, so this is nice, but okay, but this is just a tree-level computation. So you might think this structure may break down if you go to higher loops, but surprisingly, this structure persists even at higher loops. For example, people did a computation. Yeah, actually, it's a MIT. Maybe it's a MIT. No, you did the one-loop computation. So it's not a MIT. Maybe not you. Yeah, well, there is probably, yeah, maybe one loop is not a MIT, right? Okay. Sorry. Yeah, I think, yeah, okay. So there are people who did a one-loop computation, and surprisingly, even if you go to one loop, this structure persists. But of course, if you go to one loop, the result is not the same. And the only part you need to modify is actually that function h. Well, of course, you also need to modify the E to IP or some S matrix, but they are already known in the literature in the study of two-point function. So the point is that also for one loop, this structure persists. And, well, there is certainly one loop correction. So once you modify h, you get the right answer. But funny thing is that if you take HUV, first of all, if at tree level, if you take HUV and consider the ratio between HUV over HVU, then at tree level, it becomes SUV. Well, this is easy to see. Remember that H is this guy. And if you recall what the S matrix at one loop was, then you can easily verify this relation. And surprisingly, even at higher loop, this relation still holds. So this was experimental observation. So this means that this structure of bipartite summation or sorry, bipartite partition should be telling us something deep about the computation of the three-point function. To understand what it is telling us, let's go back to this tree-level reconstruction picture. So now there is some connection with a pair of pants. So if you look at this diagram, topologically, if you fill in the faces, so these lines are propagators. And if you fill in the faces, you get this kind of Riemann surface with 3 holes here and here and here. And let me also remind you what we did by summing over the wave function. What we did by summing over the wave function was we basically summed over the wave function on this segment. And the result is given by bar-type partition. So and the segment, if you draw it on this pair of pants, basically corresponds to this line, this curve. So this is the left edge, and this is the right edge. And the fact that the final result is given by the sum over partition means that essentially, finally, the result is given by sum over partition. And so essentially, the left edge is here. So you are basically like distributing the particles between this point or this point. So you have like an alpha particle here and alpha bar particle here. So this is geometric understanding what this is telling us. And of course, at this moment, you don't quite understand why I'm talking about the Riemann surface, probably. But if I don't have time to tell about it. But if you use the ADS-CFT, then this surface, which you get by filling the faces, precisely corresponds to string wall sheet in ADS. So it's actually natural to think about it as the surface with 3 holes. Now, if you look at the final result, the particle living in alpha and the particle living in alpha bar are not directly talking to each other. So it seems rather natural to kind of, well, it will be better if there is a kind of way of like getting alpha and alpha bar apart, making alpha and alpha bar apart. Because if you just draw this picture, like everything is on a single surface, so it seems a bit unlikely that alpha and alpha bar do not talk to each other. And the way to make it clear that alpha and alpha bar do not talk to each other is to cut this surface like this. And if you cut this surface, what you get is a pair of hexagonal patches where this part corresponds to this part, and this part corresponds to this part. Okay. And now the particle alpha is living on the first hexagon, whereas the particle alpha bar is living on the second hexagon. Okay. And surprisingly, or rather intriguingly, this is precisely the way you make a pair of pants. For example, if you look at the pants, what you are wearing, then you can see that there are 3 seams here, here, and here. And if you cut it open, you precisely get 2 hexagonal patches. So the way we are doing the computation was actually mimicking how the tailors make pair of pants, although we are not aware of it. Okay. So all right, this was supposed to be a joke, actually. Anyway, so now my claim is that this H, this important H I was talking about, is essentially like a associated with each hexagon. So let me be more precise about the conjecture. So now I'm going to present the conjecture for the finite coupling structure of this three-point function. Let's see. Okay, so the conjecture, let's call it hexagon conjecture. So the three-point function, okay, let's denote the three-point function using this pictorial notation with one non-trivial operator. So you have like a set of particles whose rapidities are ui's, is given by sum over bipartite partition. So essentially, what I'm going, okay, actually, I didn't have to erase this probably. Times, okay, so this times e to I p alpha bar L13, where L13 is essentially the length here, or length here, which is completely determined by the length of the operator, times S reorder, which I just described above, and these two hexagons. So hexagon with particles alpha, hexagons with particle, so there are actually several particles, alpha bars. And the conjecture is that once we replace everything, this got, yeah, I shouldn't use this one. Okay, so once we replace this by this is the finite coupling expression which I talked about so yesterday, and also we also need to replace this with the finite coupling Nicholas's S matrix, or Bizard S matrix. Then it should give the full answer. That's the conjecture. But of course, you should complain because I didn't yet tell how to compute these hexagons. And in the last 15 minutes, I'm going to explain how to compute these hexagons using actually the same idea as I used in the previous lecture. But before doing that, is there any questions so far? Yeah, anyway, I need to erase this, so. Yes?
Again, the appearance of L13 in this diagram?
Okay, so L13, okay, well, L13 is essentially, the definition of L13 is very simple. L1 plus L3 minus L2 over 2. This is the number of weak contraction between O1, operator 1 and operator 3. And it's completely determined the length of the operators. So it's just a well-defined number. And the reason why I'm drawing this here is because if you draw a tree-level weak contraction, then the number of weak contraction between this guy and this guy is precisely L13. So let me then remind you what we were discussing in the last lecture. So in the last lecture, I was saying that in order to understand the finite coupling behavior of n equals 4 super mu 3, we need to make a clever use of the symmetry, in particular, the little group for the two-point function. And in addition, we need to consider the gauge transformation, especially which becomes the large gauge transformation when you consider the infinitely long operator. So what I'm going to do now is essentially the same. But now, the object we want to study is not the two-point function, but the three-point function. So the starting point is to understand what is the little group. Well, actually, the starting point is to understand what is the analog of the rest frame. Oops. Okay, so essentially, I have just given you the rest frame. So the finite coupling analysis. So step 1 is to find the rest frame. And I declare that the rest frame for the three-point function is as follows. So you consider operator z to L1 here at position 0, and you put z to z twiddle. Okay, I changed a little bit the convention here. And then I put z bar to, okay, let's call it L3 actually. Z bar to L2 at position infinity. So I declare this is the rest frame for the three-point function. So once you determine the rest frame, so as in the case of two-point function, essentially this doesn't contain any field insertions. And idea is to start from this configuration and then start adding some impurities inside this trace to get the more non-trivial three-point function. And once you identify okay, by the way, this is the three-point function of BPS operator for those who knows the supersymmetry. And this is actually protected, so it's actually tree-level exact. Now, once you determine the rest frame, the step 2 is to identify the little group. In the case of two-point function, the little group was PSU 2/2 squared. So now we need to understand how this little group is further broken to something else. And again, it's very useful to first consider the bosonic part of the little group. Let's consider the space-time bosonic part. Now I have operator at position 0 and position 1 and positioning at infinity. And by drawing a line which connects three operators, you can actually see that this choice of three operators specifies one line inside R4. So when you talk about the little group, you need to find a transformation which keeps this line untouched. And of course, it's very simple. Because you are in 4 dimension, the little group is SO3. So this is a space-time little group for the three-point function. And let's also consider, okay, there is one blackboard over there, but so I first need to erase this. So let's also consider the R-symmetry part of the little group. And that's actually also easy. And the reason is, well, I just need to know how many scalars I used to construct this three-point function. So let's count it. So I used phi1 plus I phi2 here. So I already used 2 of them. And this z twiddle, okay, you need to remember the definition, but it's z plus z bar minus y bar. And z is phi 1 plus I phi 2, and y is phi 3 plus I phi 4, which means that I have actually phi 1 plus I phi 4 here. So now it's clear that I'm using 1, 2, 3 scalars to construct this 3-point function, which means that there is a residual symmetry which rotates phi 3, phi 5, phi 6. So this is again SO3. And there should also be some supersymmetry, but it's a bit hard to explain what the supersymmetry is in the remaining time, but you can probably guess what group you get after considering the supersymmetry analysis. And the answer is very simple. And the answer turns out to be what? Turns out to be, yeah, I should use that blackboard. And the answer turns out to be diagonal subgroup of PSU2/2 squared. And you can clearly see that there are two SU2s which account for the bosonic part of the symmetry. And this diagonal subgroup, so remember this one contains L rotation, R symmetry rotation, and also L dot and R dot, which are the PSU2/2 left. Sorry. So the original symmetry group had 2 copies of PSU2/2, and there are also supersymmetry and superconformal. And this is broken down to L plus L dot, R plus R dot, and Q plus S dot, and S plus Q dot. So these are the generator of this single PSU2/2. And furthermore, we know that this gets centrally extended when you consider the large gauge transformation. And then you can also ask how this gets also kind of extended. Well, it's actually easy to see by computing the anti-commutator. And then you discovered, in addition to these guys, there is one combination of central charge which survives, which is P minus K. So the definition of P minus K, I don't have time to recall you, but I think you can find it in the notes of the previous lecture. So this is a little group of the 3-point function. And now, in the remaining 5 minutes, I'm just going to briefly describe you how to determine or constrain the hexagon by using this little group. Again, so okay, let's again consider the simplest case where you have one particle on the hexagon. So the particle here, of course, carries definite rapidity or definite momentum. And in addition to that, as I explained in the last lecture, each particle belongs to the bifundamental representation of PSU2/2 square. And now what you need to do is to find some tensor which have 2 indices and which is invariant under the diagonal PSU2/2. And for simplicity, let's consider the SU2. Suppose you have like 2 SU2 indices and which act separately to A and A dot. And then you are asked, what is the tensor structure which leaves this, which is invariant under the diagonal transformation of SU2/SU2? And the answer is simple. The answer is, of course, epsilon tensor. And it turns out there is a kind of supersymmetric generalization of epsilon tensor. And this is precisely what I need to put here. But of course, this symmetry analysis doesn't tell you what is the overall factor. So this is, at this moment, unfixed. Now, I can also ask what is the two-particle structure. So now you have two particles on the hexagons, A dot and B dot. Again, your task is to find some tensor invariant under the PSU2/2 diagonal symmetry. But in order to, so this is like a tensor with 4 indices, which is invariant under a single copy of PSU2/2 diagonal. But I need to recall you that yesterday, at the end of my lecture, if you consider the 2-2-2 scattering amplitudes, which have essentially 8 indices, then the matrix structure is completely determined, and it's given by something like this. So this is precisely the BiZS matrix. And what this is telling us is actually if you impose the invariance of single PSU2/2, and if the object has 4 indices, this is precisely the only structure you can draw, you can write. So this is the two-particle S matrix. And this is S hat in my notation. So you can immediately say that the object appearing there should be related to the S hat. But if you work out the detail, okay, I shouldn't have used this one. If you work out the detail, then it's actually indeed true that you get the S matrix, but the final result is something like this. So you have S hat, A, B, U1, U2, C, D, and then you contract this with epsilon tensors, which is C, C, A dot, epsilon, D, B dot. Okay, so, and then there is unfixed overall parameter, which I denote by H, U1, and U2. Actually, in my notation, I should also put square root of U1. Well, this is just a convention of how to parameterize the overall factor. Okay, so this is the only tensor structure you can draw. And then the last question is how this generalizes to multiparticles, because once you know the multiparticle tensor structure, then you can basically write down our conjecture more precisely. But let me very briefly tell you about the multiparticle structure, but before doing that, I should introduce some pictorial notation in which epsilon tensor is depicted in this way. So this means that you contract 2 indices by epsilon tensor. And in this pictorial notation, this S hat is something like this. So this S hat is you have A, B, A dot, B dot, and then you first act the S hat S matrix, and then you contract it with the epsilon tensor. So this is a pictorial notation of the tensor structure for the 2 particles. Now, we are getting to the final point in which you can actually write down hexagon conjecture more precisely. So the final point is what happens to the multiparticle. So this is always the difficult question because typically symmetry is very useful for 1 or 2 particles, but it's often not so useful to constrain the structure uniquely for the multiparticles. And in the case of two-point function, we basically assume that there is integrability and the S matrix factorizes. So what we do here is basically very similar. So the conjecture for the multiparticle is as follows. Now it's very cumbersome to write the tensor structure explicitly in terms of tensor. So now I start using the pictorial notation. So you have A1, A1 dot to M, AM, AM dot. So I would claim that this is for, so I runs from 1 to M. And first of all, I have square root of mu I. And then there is an overall factor H U I U J. And then finally, I have the tensor structure, which I denoted by the pictorial notation. So you have, what you need to do is to split the indices into dotted indices and undotted indices. And then connect these dots in this way. And then, so roughly speaking, this picture means that whenever you see the intersection, you multiply by Bizert's S matrix. And then when you contract, you basically put epsilon tensor. So this is the conjecture for the multiparticle hexagons. Now we are almost there, but we don't know how to determine these two quantities. Unfortunately, I don't have time to tell you how to determine it, but I should just mention that this can also be determined by imposing crossing and unitarity. So this was also the case for the S matrix, two-particle S matrix at finite coupling, and the same argument applies also here. So, and once you determine this once you determine this mu of H, then you can plug in this structure to the conjecture of hexagon conjecture, and then you can start computing the three-point function at finite coupling. So this conjecture was made in 2015, and after that there are like numerous checks, especially against the weak coupling explicit computation. And at this moment, this conjecture was checked up to 4 loops, I think. Yeah, it's the paper I wrote actually, but yeah, the conjecture was checked up to 4 loops. So maybe it's a good time to stop here. But so essentially, the point or main message of my talk was if you use symmetry, especially like a little group and the large gauge symmetry, and if you further impose some nice properties coming from integrability and also crossing and unitarity, you can often completely solve the system. And that's actually very exciting because maybe we are discovering the first example of interacting 4-dimensional gauge theory which can be completely solved. Thank you very much.
So my question might be a little naive, but what happens if you choose L1, L2, and L3 such that L13 is 0?
Okay. L becomes 0, exactly 0?
Yeah, L13 becomes 0.
So when L13 becomes 0, you need to worry about the mixing with the double trace operator. So far, the computation was only about only in the large n limit, and basically, in most cases, you don't have to worry about like a non-planar effect, but some non-planar effects shows up in this particular limit. So yeah, must be larger than 0. Yeah. Okay. Okay, so this is actually, okay, so what I explained today is actually not the most recent development of this story, and because I only talked about a 3-point function, but you can basically do the same for the higher point function. For example, if you have a 4-point function, pictorially, it is sphere with 4 holes. And then you can cut it, this sphere with 4 holes into hexagons, and then glue it back together. And in this particular case, you have 4 hexagons. And we know that the 4-point function depends on the cross ratio, and the cross ratio actually turns out to be related to some chemical potential, which appears when you glue 2 hexagons together. So this was the most recent development.